Next we discuss problem number 9. It says at 298 K, a 0.1 molar acetic acid solution is 1.34% ionized. Calculate the ionization constant Ka of acetic acid. So here the degree of dissociation, of acetic acid we say alpha is 1.34%, so 1.34 by 100, so we get 0.0134. So now we consider the equilibrium. Okay, so CH3COH is acetic acid, so we are adding water here. Now it is in equilibrium with acetate ion, CH3COO minus plus H3O plus. Since the initial concentration of acetic acid is 0.1 molar, the number of moles of CH3COH ionized is 0.1 times 0.0134. So we get 0.00134. So number of moles of acetic acid, unionized acetic acid, unionized. So we had 0.1 mole acetic acid initially, and this many number of moles is dissociated. So we get 0.1 minus 0.00134. So we get 0.09866 moles. So according to the reaction, according to equation, one mole acetic acid gives 1 mole CH3COO minus mole of acetate ion and 1 mole of H3O plus ions. So we can write at equilibrium, the concentration of CH3COH is 0.09866, concentration of CH3COO minus is 0.00134, and concentration of H3O plus is also 0.00134, right. So therefore K, the dissociation constant of acetic acid, K is concentration of product right hand side. So CH3CO, concentration of acetate ion times concentration of H3O plus ion by concentration of acetic acid So if we simplify this one, we get acetate ion concentration is 0.00134, concentration of H3O plus is again 0.00134, and concentration of acetic acid is 0.09866. So if we simplify, we get 1.82 times 10 to the minus 5. Move to problem number 10. It says, given that the ionization constant Ka of HF is 3.2 times 10 raised to the minus 4, determine the dissociation for 0.02 molar HF solution. Also calculate the concentrations of all species present like H3O plus, F minus and HF, and the pH of the solution. So first we do not know the initial concentration of HF, so we consider the initial concentration of HF is C moles per liter, and the degree of dissociation of HF is alpha. So HF dissociates as HF plus H2O is aqueous, this is liquid, so gives H3O plus aqueous plus F minus aqueous. So initially we had C moles of HF and H3O plus was 0, concentration of H3O plus was 0, and concentration of F minus is also 0, was also 0. Now at equilibrium, so alpha is the degree of dissociation, so C times 1 minus alpha, this will be your C alpha, again this is your C alpha. So therefore the dissociation constant of acetic acid if we say this is Ka is concentration of H3O plus times concentration of F minus by concentration of HF. So we write C alpha times C alpha by C times 1 minus alpha. So we get C alpha square by 1 minus alpha. So we can actually write this one like before, we write C alpha square when alpha is very smaller than 1 minus alpha becomes 1. Okay. So that is the value of Ka. So value of Ka is also given here. So Ka is 3.2 times 10 to the minus 4, right. So alpha square is 3.2 times 10 to the minus 4 by C, or we write alpha is 3.2 times 10 to the minus 4 by C, and then we have to take a square root of this. Okay, so we have to take square root of this. Now we know the value of C is 0.02 molar, so we substitute it here. So we write 3.2 times 10 to the minus 4 by 0.2. Okay, so if we further carry out this one, we get alpha. So alpha will be 0.126. Now once we get alpha, we know the concentration of H3O plus right now. because concentration of H3O plus is C times alpha. So concentration of H3O plus is C times alpha. So C is 0.2. Oh, sorry, 0.02. This is C is 0.02, not 0.2. So C is 0.02 and alpha is 0.126. So we get the value 2.52 times 10 to the minus 3 moles. Similarly, concentration of F minus is also same. Yes, it will be C alpha. So again we get 2.52 times 10 to the minus 3 moles. And we need to calculate concentration of HF. Okay. So concentration of HF at equilibrium the concentration of HF is this one. Okay, C times 1 minus alpha. So C times 1 minus alpha. So C is 0.02 times 1 minus alpha is 0.126. So we get 1.748 times 10 to the minus 2 moles. These are the concentration of H3O plus, F minus and HF at equilibrium. Now we need to calculate the pH of the solution. The pH is minus log 10 base concentration of H3O plus. Now concentration of H3O plus we already calculated, so minus log 10 base 2.52 times 10 to the minus 3. So if you simplify this one, we get the value of pH. pH is 2.60. So this is the pH of the solution. Next we discuss problem number 11. It says determine the pH of a 0.08 hypochlorous acid solution with an ionization constant 2.5 times 10 to the minus 5. Also find the percentage of dissociation. So HOCl, hypochlorous acid, HOCl dissociates as, we need to first write the dissociation equation. Okay. So hypochlorous acid HOCl dissociates as HOCl plus H2O HOCl aqueous plus H2O liquid, so gives H3O plus aqueous plus ClO minus aqueous. Okay, so initially, so suppose we consider C moles of HOCl is present. So C moles present here. So there is no H3O plus and no ClO minus. And at equilibrium, the concentration of HOCl is C times 1 minus alpha. This is C alpha, this is C alpha. So here we considering C is the initial concentration of HOCl and alpha is the degree of dissociation. Of HOCl. Okay. So the Ka, the ionization constant Ka, the ionization constant of HOCl Ka is H3O plus, concentration of H3O plus times concentration of ClO minus by concentration of HOCl, right? Now, what is the concentration of H3O plus? H3O plus at equilibrium is C alpha. concentration of ClO minus is also C alpha. C alpha times C alpha by C times 1 minus alpha. Again C gets cancelled, so we get Ka is C alpha square by 1 minus alpha, and like before we can actually calculate. Okay, so we can actually calculate the value of alpha. Okay, so we can further simplify this one as C alpha square as or when alpha is very small compared to 1, then we can write 1 minus alpha equals to 1. So we get alpha is square root of Ka by C. Now we know the value of Ka and value of C. So Ka is 2.5 times 10 to the minus 5, and the value of C is 0.08. So if we calculate this one, we get alpha is 1.77 times 10 to the minus 2. Okay. So this is the value of alpha. Okay. So once we get the value of alpha, we can actually calculate concentration of H3O plus. So concentration of H3O plus will be, so concentration of H3O plus, because we need to calculate pH, right, to find the pH of the solution. So concentration of H3O plus is C times alpha. So C is 0.08 times alpha is 1.77 times 10 to the minus 2. So that is, this is the value of this is the concentration of H3O plus. Now pH is minus log 10 base concentration of H3O plus. So minus log 10 base 0.08 times 1.77 times 10 to the minus 2. So if we calculate this one, we get pH is 2.85. Okay. So this is the value of pH. Next we calculate the percentage of dissociation. Okay. So next, in order to calculate that, we need to basically calculate the unionized HOCl. Okay. The unionized HOCl is the concentration of unionized HOCl. So this is C times 1 minus alpha. This is at equilibrium we have. So C times 1 minus alpha. So C is 0.08 times 1 minus 1.77 times 10 to the minus 2. So again, see, the value of 1.77 times 10 to the minus 2 is very small compared to 1. So we can write the unionized concentration of HOCl is 0.08. Okay. So percent dissociation is 1.41 times 10 to the minus 3 by 0.08 times 10 to the times 100. So we get 1.76%. Okay, so this is the value of percent dissociation of HOCl here. Next we move to problem number 12. It says, find the pH of the resulting solution obtained by mixing equal volumes of two acid solutions A and B with pH values of 6 and 8 respectively. This is an interesting problem. Okay. So we consider, okay, not H, we consider acid solution, so we consider pH here 4, not 8. This is pH 6 and 4 we consider. So pH of solution A given. Okay, what are the data given? So given pH of solution A or acid A, pH of solution of acid A is 6 and pH of solution of acid B is 4. So So pH is minus log 10 base, okay, concentration of H3O plus, right. This is pH. So pH 6 means the value of the concentration of H3O plus here is 10 to the minus 6 molar. Similarly, concentration of H3O plus here is 10 to the minus 4 molar, right, pH 4 means. Now we are mixing equal volume of two acid solutions. Suppose we are mixing one liter of acid solution A with 1 liter of acid solution B, because equal volume we are mixing. So total volume is now 1 plus 1, so gives 2 liter, right. So concentration of H3O plus in the mixer, if we consider, so what is the concentration of H3O plus in the mixer? So we have 10 to the minus 6 of A plus we have 10 to the minus 4 of B in 2 liters. So we get 5 times 10 to the minus 5. So this is the concentration of H3O plus in the mixture. Okay, so if we need to calculate the pH, right? Yes. So for okay, so the pH of the mixture is of the solution mixture is so pH is minus log 10 base concentration of H3O plus, so minus log 10 base 5 times 10 to the minus 5. So if we do it, we get 4.3. So pH of the resulting solution is 4.3, not 5 here. Next we move to problem number 13, which says a 0.1 molar solution of bromoacetic acid is 0.132 ionized. So alpha is 0.132 here. Determine the pH of the solution and the pKa value of the bromoacetic acid. So given the degree of ionization of bromoacetic acid, alpha is 0.132, right. Now concentration of, because concentration of, therefore concentration of, okay, so we consider the reaction here. Okay, so the equation or bromoacetic acid ionizes as bromoacetic acid in aqueous, and then H2O liquid produces BrCH2COO minus aqueous plus H3O plus. So if again initial concentration is C, so initially we have C moles of bromoacetic acid and then 0 moles of acetate and 0 moles of H3O plus, and at equilibrium we have now C times 1 minus alpha gives C alpha times C alpha, right. Okay, so now where C is the initial concentration of bromoacetic acid. And alpha is the degree of dissociation or ionization we already considered, okay, already considered here. Okay, so at equilibrium, these are the thing, then we write Ka is the acid dissociation constant of bromoacetic acid Ka is concentration of BrCH2CO minus times concentration of H3O plus by concentration of BrCH2COH. And this is C times 1 or C alpha. So numerator will be C alpha times C alpha by C times 1 minus alpha. So C again gets cancelled, so we get Ka is C alpha square by 1 minus alpha. So we can write this one as, okay, so if we substitute the values of alpha here, so we write C is 0.1, so this is 0.1 molar. So 0.1, alpha is given 0.132 the square and then 1 minus 0.132. So if we calculate this one, we get the value of K becomes 2.01 times 10 to the minus 3. So this is the value of K. Now Pk is minus log 10 base K. So we substitute now the value of K, so we get minus log 10 base 2 times 10 to the minus 3. So we get the value of Pk is 2.7. Next we need to calculate the pH of the solution. Okay, for the pH of the solution we need to know the concentration of H3O plus. Okay, the concentration of H3O plus at equilibrium is C times alpha. So C is 0.1, alpha is 0.132. So the pH is minus log 10 base concentration of H3O plus. So we get minus log 10 base 0.1 times 0.132. So we get the pH of 1.88. So the pH of the solution is 1.88 and the pKa of bromoacetic acid is 2.7. Okay.